I'm Tim Ventura, and we're joined today by Dr. Ken Wharton, a professor of physics and astronomy at San José State University. Ken's research is in the field of quantum foundations, with a current focus on time-symmetric and causally neutral models of physics, working towards the ultimate goal of reframing quantum theory in a manner fully compatible with general relativity. He's also written a number of popular science pieces, appeared in venues such as New Scientist, Aeon, and Nautilus. So Ken, welcome, sir. Today we're
Thank you,
talking about,
Tim. Thank you for having me here.
absolutely, we're talking about time and causality in physics. So let me begin with a recent article in The Conversation that you co-authored discussing the 2022 Nobel Prize, quantum mechanics, non-locality, and of course, causality. Could you tell me a little bit about what inspired you to write this?
Well, part of it was the first Nobel Prize in quantum foundations, but the other part of it is that there's a new team in quantum foundations, kind of a new up-and-coming, thriving research community of people interested in this maybe offbeat, but more and more people are interested in this particular offbeat subset of quantum foundations, and so bringing it to people's attention that there's a new player in town that people should pay attention to.
Yeah, well, and I will put links into all of the articles. There was a Vice article. That was the one that I'd kind of gotten started with. It took me back to an article in, again, The Conversation, and then there were some other references from there as well. But basically, what you've written in this piece is that many people believe the Nobel Prize winning experiments challenge locality. Others are calling it death by experiment for local realism. But you're offering kind of a third alternative, which is this idea of retrocausality, that events in the present can affect the past. Can you describe that a bit for me?
Yeah, so I mean, part of it is just how do you describe causality? And we've actually come a long way in understanding what we even mean by causality in the last 20 years or so. And what you mean by a physics model that has causality in it is just that if there's some number coming in from outside the model, like a setting of an experiment that you don't model why that setting is the way it is. It just comes in from outside the model. And then you see, oh, there are these things correlated with that setting. Like if I turn the setting to 1, these things happen. If I turn the settings to 2, these things happen. That's causality, right? That's sort of the input is some number coming into your model, and the output is something correlated with that. So all retrocausality is looking at events before the input goes in. So in the classic experiment we're talking about in these articles here, these entanglement experiments, at the end of the experiment, you make a setting choice of how you're going to measure it. And if there's something before that event that's correlated with how the setting is arranged, then it's a retrocausal model. We don't use those normally, but maybe it's what we need to make sense of quantum theory.
Yeah. Well, what this takes me back to, I believe, are called Feynman diagrams, right? Where you've got particle interactions and you'll have two particles here and you'll see little arrows and then, they form a new particle or something along those lines. There are lots of different interactions. And one of the things that I've read is that these things can be played in reverse, right?
Sure, but there's a difference between being able to play something in reverse and actually having the input in the future. So for example, I can have a video of two particles colliding and then going away, and I can play that video in reverse, and it looks like this. And both seem to obey the laws of physics. And so now I wouldn't say that was causal or retrocausal. That's just a bunch of facts played one way or played the other way. Where the causality would come in would be to say, well, what do I have control over? Usually what you have control over are the incoming particles. So I'm going to set those incoming particles to be just so. And look, oh, the outcoming particles are correlated with my setting. So that's forward causal. What you don't have in Feynman diagrams explicitly is a point at the end where you have control, right? You don't have control of some knob at the end of a Feynman diagram. So I wouldn't say that Feynman diagrams were retrocausal. I would say that they were generally time symmetric.
Time-symmetric. Okay.
Yes.
Well, so from what I understand, retrocausality is supported by Aharonov's two-state vector formalism, right? And I have heard that this approach solves some of the challenges that traditional quantum mechanics struggles with. Does that sound correct, or am I kind
Well,
of...
that's debatable. I mean, some people will tell you that there's nothing you can get out of this two-state value formalism, two-state vector formalism that you can't get from ordinary quantum mechanics. But the people writing about it are saying, oh, this gives us better insight into maybe how to make quantum mechanics more time-symmetric than it seems to be, and maybe insight as to what's really going on when we're not looking. They are these things called weak values that you can just barely measure, and you can argue that maybe that's really what's going on when we're not looking, are these weak values. The people who have developed that into a full-blown retrocausal model tend to be well, Aharanov talks about retrocausality and says maybe that's what's going on. And then there are people like Rod Sutherland who have kind of looked at these weak values and said, oh, maybe that's really what's happening. And those really are dependent on how you choose to measure the system in the future, the weak values. So if you think the weak values that you can just barely measure are real, even when you don't look, then yes, then there would be retrocausality in those models. Yeah.
Ah, okay. Well, and I want to mention another one also. And again, I am not a physicist by any stretch of the imagination, right? And it becomes obvious when I get into in-depth stuff like this. But another thing I've read about is the block universe model, potentially being an approach to physics that offers solutions for issues like negative time interactions that, again, traditional interpretations struggle with. Do you think block universe might be maybe another approach, I guess, that'll pick up steam in the future?
Okay, so the block universe isn't really a model. It's just really a framework for thinking about events that happen in space and time. So if those viewers that don't know what a block universe is, you can imagine writing down the position and time of every event that ever happens in the universe. So position, you need 3 numbers, right? I mean, maybe on the surface of the Earth, you need latitude, longitude, and elevation, but maybe you just need X, Y, and Z coordinates. But you also need to know when something happens. So you need a 4th coordinate, time. And so every event that ever happens to you or me, we can assign a X, Y, Z, T, a 4-dimensional coordinate to. And then the array of all those events is sometimes referred to as a block universe. It's a way to organize and frame every event that happens in space and time in, I guess, technically it's a 4-dimensional block, which is hard to picture. And so usually on a picture, you'll see like maybe time going up and 1 dimension of space going to the right, and you'll see a static picture on that diagram of something representing a bunch of events in space and time. It's not really a model, just so much as, okay, let's take things we know happened and put them on this diagram. And I absolutely think that is the right way to think about time.
Oh, okay, good.
It is the right way to think about time. And sort of Einstein developed both special and general relativity in this framework, where this block universe framework, and you can't really make sense of, certainly you can't make sense of general relativity without the block universe.
Yeah, well, it's intriguing. I mean, over the years, I've read so many different approaches to it, and I guess that's not surprising. I mean, part of physics is pushing the boundaries, right? And conceptually, I think it helps to push those and then say, look, here's a hypothesis, and does the data fit with this? And
the idea of, I'm going to take all of this data and represent it in this way. That's not so much a hypothesis as this is a useful way to take everything and arrange it. I guess to the extent that there's a hypothesis, it's that, oh, and there's nothing else that's missing from this diagram. And that I would push back with some people. A lot of people don't like the block universe because they feel like, okay, sure, I can put all these events here and they're all arranged in this big block, but it's still missing something. And what it's missing is any causal story. It just is a bunch of facts, right? The causation actually comes in differently. And so we can talk about the interplay between time and causality, but when it comes to time, I'm all for representing everything on a block universe. But when it comes to causality, you need to think about it in terms of the way I mentioned, where you're, okay, but what if this were different? What if in the block I had instead chosen this for breakfast? Then in my model of reality, I would have eaten a different breakfast. And that some people call them counterfactual block universes, or, because I didn't have this other thing for breakfast. But when we have physics models, that's what we do. We imagine, well, what if this were different? What else would have been different? That is missing from the block universe. And we need it in our physics models.
Yeah, and it's interesting because, and you're the causality aspect of this, I think, is a whole nother can of worms, right? And I know that that's an area that you are very deep into. I mean, I'm starting out just looking at time itself. Like the next question, I'll just kind of skim through this. I read about a physicist who wanted to break time up into basically a series of still frame images, right? And he said, instead of a continuous flow like a river going downstream, he said what we should think of time as is a series of pictures, snapshots, and they stack together and they happen so rapidly, right? Almost like maybe like a Planck length for time or something like that. And so there are all of these different ways that people are trying to look at time. And then on top of that, you're looking at causality. But
okay, well, let's talk about the slices first before we get to causality. So I mentioned the block universe. So you could take the block and slice it up. Like you could, okay, I want this moment, and I want this moment, and this moment. And you can slice it up and take all those and call them still frames. And it's just a different representation. There's no different from the block. It's just, taking it into a different representation. I could take all those still frames and stack them up and make a block again, right? Now, what you can do with the block that you can't do with the still frames is I can slice it at a different angle. And that's one of the things that Einstein showed with this theory of special relativity, that there's actually no one special angle to slice the block at. You could slice, one observer might slice it at this angle, another observer might slice it at that angle, and get a bunch of different frames that seem to be inconsistent with the other person's slice. But it turns out if you put them all back together, Einstein showed, oh, it's all the same block. And so this is one way where the block helps you make sense of all these slices if you stack them up in time and put them together and view them as a whole rather than as a series of events.
Yeah, well, and so as you mentioned earlier, though, causality is kind of missing from this, right? Could you describe that a little bit?
Well, so where causality comes in, I've already mentioned the idea of an input from outside the model. And so usually, certainly in my field of research, where I'm trying to make sense of a particular quantum mechanics experiment done in the laboratory, I'm not like modeling what happens outside the laboratory, right? In fact, I'm not even modeling the experimenters. I'm just kind of modeling a few particles, trying to make sense of what's happening. And so from outside my model, the few particles comes causes. What do I mean by that? I mean, well, this experimenter, sets this dial to 4. And I'm not modeling that, right? That's coming into the model. That's a cause. And then I can see, well, what's correlated with that number 4? And, oh, if it were 3, then these things happen. If it were 4, then these things happen. So that's causation. The only twist with retrocausation is I'm actually considering models where events in the past are correlated with the setting. And you might ask, well, why even consider that? We didn't ever see anything like that, right? You probably have never seen a situation where your decision of what to do is correlated with what happened yesterday. But what pushes us to it is the weird, counterintuitive, real life things that you see in quantum experiments, and trying to make sense of it pushes you to, well, one thing we know for sure, the one thing everyone in this field can agree on, is something counterintuitive is going on, right? One of our intuitions is wrong. And maybe it's our intuition of causality that's wrong. Maybe that's why it seems so weird to us, because at some hidden level, our notions of causality just are wrong. And as far as, they're not wrong in the sense I described it, but they're wrong in terms of the time order we expect for the causal effect. We expect the causal effects to have happened in the future of our influence. We do not expect them to happen in the past.
Yeah. Well, for the audience, let me invoke the no DeLoreans rule. I'm going to put the no DeLoreans rule out there right now. But
no time travel.
no, no time travel. I'm trying to keep science fiction out of it
people
for
might
right
ask,
now.
wait, how can you have retrocausality and not time travel? Isn't that the same thing? But you're right, there is a subtle difference. And the subtle difference is retrocausality, you just have to have some event correlated with your future choice. Time travel, you have to have some observable event correlated with your future choice. So you need a retro signal. The only way to have retrocausation without time travel is if the effects we're talking about are hidden. If the effects are hidden down in the level of quantum uncertainty, and you never knew what they were to begin with, then it's safe to have retrocausation, because then you never get any time travel.
Well, I think another aspect of it also is all of this is happening at the subatomic level, right? And so maybe potentially someday, and this led me to thinking, I guess, when I was writing the questions, because, when this stuff is, again, when you're working on this, right? I mean, when you're looking at the physics, you're looking at that subatomic level. But then when you get into things like quantum computing, right, it can scale. It takes a lot of work. There are issues with, decoherence and things like that. But I would say, as of right now, we're looking at basically subatomic particles, right?
We are, but don't conflate that with the idea that we're just talking about very small amounts of time. Because when you do an experiment, it can involve seconds. You can send these particles down a fiber optic cable, hundreds of kilometers, and that the retrocausality to explain a quantum experiment would have to extend all the way back down that 100-kilometer cable. So in that sense, it's not microscopic, but it is microscopic. It is subatomic in the sense that we're talking about the only parameters that need to be retrocausal are hidden inside these, whatever a particle is, right? They're hidden down at the level of quantum uncertainty. And so, yes, they're very, they're subatomic hidden variables, as the terminology goes.
Now, since you mentioned fiber optic cable, do you think that something like this, I mean, obviously with further study and technology behind it, could be used for something like time backwards communications?
Well, I think no. I think that all the if it turns out that the best model to explain quantum experiments is retrocausal, I think it will be one where all the retrocausality is hidden, where there's no retro signaling. If there was, you get all sorts of paradoxes. Pick your favorite time travel paradox movie, and you can avoid all that, all these paradoxes, just by having something hidden at some level of quantum uncertainty. And you say, okay, there's hidden retrocausation, but no backward in time and no faster than light communication.
Okay. Yeah, I kind of get where you're going. So again, I'll go back to my no DeLoreans rule. I wrote that in my notes twice. I was like, make sure to mention that, just to kind of keep things on track here.
I mean, I guess you could come up with a model where there was retro signaling, but I would argue it would be a bad model because it doesn't describe our universe. Our universe doesn't have any retro signaling in any quantum experiment or classical experiment. We've never seen it. And so if you're going to put that in your model, it seems to me like a mistake. It seems to me like, well, we got to model what we see, and we don't see any backward in time signaling.
Yeah. Now, do you think that something like this plays a role in entanglement, right?
Yes.
Okay.
Okay. Now, where do we start with entanglement? Do we?
Well, yeah, and again, I guess where I'm coming from is, that there's a lot of, I'm approaching it somewhat from a technology background, right? But one of the areas that I've been focusing closely on lately is quantum communication, and not necessarily superluminal approaches, but just regular encrypted quantum communications technologies that are being developed, and then quantum computing, right? Which is also, both of these areas are moving forward very rapidly.
And they both use quantum entanglement, right?
Yeah. So, one of the things I kind of wondered about was, does this retrocausality, could this open new doors for quantum computing and quantum communication?
Yes. I think it probably will. once we have a fully working model of quantum phenomena, but we don't have it. So that's, even though we have certain quantum events that we can model with a retrocausal model, certain entanglement events, and maybe we should talk about entanglement in a minute, but even once we get to the point where we can model other events, other quantum phenomena with a retrocausal model, at that point, the question is, well, what use is it going to be? So, and I don't know, the way I think about it is that, in the history of science, every time we've kind of drilled down to a deeper level of understanding, there have been new consequences and new predictions and new experiments that you could check to see if that's right. And I don't see why this would be any different. But raise the question, well, what's going to be different? And I think if there's hope for some interesting breakthrough in quantum computing that follows from this research, I think what it would be is that, well, now we got to let's talk about how quantum computing works. So in quantum computing, you have a bunch of entangled particles. Maybe we should start with entanglement and then get the quantum computing.
Yeah, no, go for it.
Okay, let's do entanglement. So remember, we talked about the space-time diagram. So let's do time going up, and let's do space going to the right here. And on a space-time diagram, your most basic entanglement experiment looks like a V, in that what's happening down here is you're creating two entangled particles through, we don't have to talk about how you do that, but you create these two particles, and then you send one over here and one over here at later time. So on a static space-time diagram, it looks like a V. Now, there seem to be all sorts of strange correlations between what's happening at this wing of the V and this wing of the V that are not explainable through sort of conventional common cause explanations. So what is to explain these weird experiments? The non-localists will tell you that something over here is somehow influencing directly something over here. Maybe there's some faster than light communication, like instantaneous message going back and forth. It's hidden. It's also hidden. You can't send a signal with it. Or maybe a wormhole opens up. People talk about that, right?
Yeah, I've heard that one as well.
So that's one way to account for it. The retrocausal way is to look at the whole V and say, wait, they are connected. Look, they're connected through the past. And so when Alice or Bob or whoever it is turns the knob at the wing of the V over here, if that's correlated with something down here at the base, and then that's the path. So the influence is not faster than light. It's on these slower than light paths. And to the extent we can talk about things moving on this diagram, which you really shouldn't do, the diagram is all there, but you can talk about causation. You can say, if this were different, then this was different down here, and this would be different over here. And you now have a mechanism to explain entanglement that doesn't require anything going faster than light.
Okay. So in terms of quantum computing, then maybe this could bring it out of some of the maybe this could I guess eliminate some of the mystery involved with how it solves equations.
Well, okay, so I certainly could absolutely eliminate the mystery, but what usefulness might come out of this to somebody on the quantum computing side? In the quantum computing side, you have many entangled particles, and every time you add one more entangled particle, you double the size of this quantum state that describes everything. And so if I have 50 entangled particles, I have this just enormous quantum state because I've doubled it 49 times. And you add one more, you double it again. You add one more, you double it again. And it grows out of hand. And so people can't model these on classical computers. They are just these enormous states. In the retrocausal model, though, that's not how it would work. Every time I would add one more entangled particle, I would just have one more particle. It would be like just, okay, there's one more, and now one more. You don't keep doubling it. What does double or grow exponentially is the number of connections you can have. So now instead of V's, you might have W's, right? You might have crazy W's that keep interconnecting, and you get a really complicated space-time diagram, and you have to solve it all at once in these models. So it's still hard to solve. It's not like going to speed up our quantum computing ability, but it would, one, keep down the size of your state space. It wouldn't be growing exponentially every time you add one more particle. And there might be other techniques to solve. We have all these ways to solve math and physics problems. Some are these problems called minimization problems, where instead of starting at the beginning and computing what happens next, you just look at the whole thing and you minimize them. The way a retrocausal model worked would almost certainly be of that second sort, where you would look at this whole big network of qubits interacting, and you would minimize or quantize some all-at-once global quantity, like this thing called the action. And it's a different way to solve it. It might end up being faster in certain problems because it's just a different way to solve a quantum circuit.
Yeah, yeah. Now, I should ask if there's, and I know this is, I feel stupid even asking this, but is there anything that you could consider proof that retrocausality is happening? You know, and I know, and I know that's a horrible question to ask, because
it's hard to prove anything in science, right?
Yeah.
So yeah, I mean, kind of the way science works is you falsify models. So, if there's a retrocausal model that has a new prediction, as I think would be inevitable if we had a deeper hidden variable description, then there would be things to test. And you could do the test and discover the model's wrong. Oh, okay, falsify the model. Or it doesn't falsify the model, it doesn't prove it's right, but it's evidence, right? That's how science works. And then maybe someone will tweak the model and change it, and there'll be differing predictions. And then you can pick which one matches reality. That's the way science works. So I don't see a way to kind of prove it, but I do see testable hypotheses on the horizon.
Okay, well, and that was kind of what I was driving towards. And I mean, based on what I've seen in science in the past, it seems like this approach will keep getting developed by yourself and others, right? And you basically work through different challenges in it, and it'll kind of wait out there in the wings. And at some point, like, a test will arise that can only be solved by this, and and then once again, we see it in the headlines where it's like, okay, normal physics fell on its face, but retrocausality easily solves this. And then it may start to gain the traction that it deserves in the scientific community, right?
Well, whether it deserves it or not depends on how the experiments come out. But if the experiments came out that way, then yes, then it would deserve it and it would get the attention. I mean, I guess right now, the people who are just, building a quantum computer probably couldn't care less about what the interpretation was. They just want their quantum computer to work. But the people that do care, or should care, I should say, about what's going on under the hood of quantum theory, which is really just this big black box that we don't know why it works. We put in the inputs and get out the output probabilities, and we don't know what's going on inside the box. But suppose there was like a model that you could look in the box and see what was going on. The people that would care would be the people that can't get quantum theory to play nice with gravity and space and time. Because if these retrocausal models are right, and you don't need faster than light or weird outside of space-time influence to connect the wings of the V, and everything is on a space-time diagram, and the explanation is living in space-time, then adding gravity to that picture is trivial, because everything's already in space and time, and the gravity is a story of space and time. The reason that we don't know how to get gravity and quantum theory to play nice with each other is the standard theory of quantum mechanics doesn't live in space. It lives in this giant, crazy quantum wave function that doesn't have a spatial representation. And so what do you do when you want to mix it with space, time, and gravity? Well, there's lots of ideas, but nobody knows what to do. If there was an account of quantum theory that did fit in space and time, there's a whole new research avenue opened up to get relativity and quantum theory to play nice together.
Well, I really liked what you talked about with the block universe and being able to slice it differently, which kind of answered one of my own questions in terms of relativity, right? Because, I mean, the way that it's represented, time moves different speeds depending on what gravitational field you're in. And let me see.
Clocks tick at different speeds.
Clocks tick at different speeds.
Yeah.
And so then there's this idea of retrocausality, but it almost seems like it's a moving target, right? It depends a lot on where you are, or I believe what they would call the local reference frame. So
okay, so if you're worried about clocks ticking at different speeds, that Einstein seems to have settled all that. We kind of have a good story of what's going on there. I guess where the retrocausality connects with that is, it's not so much that the block universe is allowing for time to flow backwards or anything. I'm not even sure that makes any sense. I'm not sure it makes sense for time to flow forwards, right? On the block universe, you've represented time as a spatial axis. Like, this is a spatial axis, right? And so the classic blunder people make is that, okay, I'm going to represent time as a spatial axis, and then I'm going to move this around. But to move something around on it is ordinary time that's running in your head. And so now you have one time represented as a spatial axis, another time represented by something moving around, and you have two times all of a sudden, and you've kind of lost the thread as I see it. Instead, the reason people want to think about things moving around in these diagrams is what they really want to think about is causation. But you don't need anything to move for causation. You just need to imagine, oh, what if this were different? What else would be different? You don't have to move anything to ask causal questions like that. You just have to run through the possibilities. Wait, what if I set this? Wait, no, what if I set this? Recalculate everything. Nothing's really changing or moving. You're just you're checking causal correlations, right? You're checking what are the effects of my intervention. That's what you're checking.
Yeah. Well, and again, so you're describing the V, where the causation can go back to where the particles were entangled and come out the other side. And again, that solves the need for superluminality, I guess.
But nothing is actually going back, because nothing's going anywhere on this diagram. The key is, if this had been different, this would have already been different, right? So it's not like something's flowing back, because that's the thing moving on time is this vertical axis here. The idea is just that, well, what if this were that? Then this would have been this. If this were that, this would have been this. That's a retrocausal model. And it's a new thing we should be exploring. It's not, it's intuitively wrong, but we know one of our intuitions is wrong. And how do we know which of our intuitions is wrong? You can't trust your intuitions at that point, right?
Yeah. Yeah, and this stuff is beyond. This is kind of beyond the realm of normal human senses, also, right? And we run into that a lot in physics. That on these levels,
and we have learned, and through physics in the last 100 more years, that our intuitions about time are really flawed. You mentioned this notion of different reference, or we talked about different reference frames having different notions of simultaneity. We've talked about time symmetry, that like microscopic events look the same and you run them forward and backward. These are all counterintuitive, right? We didn't expect to find time symmetry down there at fundamental equations. We expected time to have an arrow, right? We didn't expect our idea of now to be wrong, but it is wrong according to relativity. There is no such thing as an objective now. So we know we're wrong about several things about time. Maybe we're wrong about one more.
On that note, let me thank you so much for your time today. It has truly been a pleasure and an honor to be able to interview you about this. Absolutely wonderful. And we have run through so many different things. I think folks are probably going to have to watch this 2 or 3 times. I know I'm going to have to go back and just rewatch and say, okay, how does this make sense? But that's wonderful. That is the best type of interview for me, is one that makes people think and really pull it apart. So thank you so much. Let me close by asking, what comes next for you, and what comes next for your work in retrocausality and time symmetry and all of these things that you've been working on?
I guess the next thing that I really want to do, and I feel like is getting close, is to have a retrocausal model that can map onto what quantum quantum computing experts, quantum information people, what they do. And when they are building their quantum circuits on paper, they have this sort of framework where you have a couple qubits, they go into these gates, like they're quantum gates, they're not like and or gates, but they're like and or gates, right? And they've discovered that you can build up any quantum circuit, no matter how complicated, with just a few basic gates. And I think that's the right way to think about it. So I'm building up a retrocausal model with a few basic gates. And if it works and if it scales, you can add another gate, you add another gate. We've cracked it open, right? You just need to get those few basic gates to work right in the model. And then you nest them together and you have everything. And so that's, I think, the next step is to get these basic quantum gates, have a model for them that works in this sort of retrocausal framework. And then I think there'll be a lot of interesting future research that could spin off of that for sure.
Wonderful. Ken, thank you again so much for your time today, sir.
Well, I'm glad you enjoyed it. And thanks for having me on.